Hello, and welcome to this AMETEK Land webinar. My name is Katie, and I will be your Global Spec moderator, and I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the speaker bio window, with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. All questions will be answered following today's webinar. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenter. With us today is James Cross. James is the Global Industry Manager of Hydrocarbon Processing, or HPI, at AMETEK Land. To read more about James today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to James to get this webinar started. So go right ahead.
Hello everybody, and welcome to the AMETEK Land webinar on optimizing fired heaters using portable Borescope thermal imagers. My name is James Cross. I'm the Global Industry Manager for Hydrocarbon and Petrochemical Industries at AMETEK Land. I'm based in Dubai, United Arab Emirates. My experience generally is in furnaces of all types in the automotive, aerospace, defense, and other manufacturing industries, and being based in Dubai in the last 4 to 5 years, more on petrochemical and refinery processes. Just to give you an idea of how infrared technology is being used in other spaces, long-wave infrared cameras are used to monitor flammable materials. That's looking for elevated temperatures in storage yards, petcoke, sulfur. We'll talk more about furnace monitoring. Flare and pilot flare detection is a upcoming process that we're using infrared cameras on, where we're looking at main flare status and pilot flare status to alert end users in the instance of a failure of any of those. And critical asset monitoring is using the Borescope or fixed thermal imagers to identify elevated shell temperatures of assets in case of refractory wear or concerning phenomena on those units. What we're talking about today is fired heaters, and our experience with fired heaters really started in steam methane reforming, because we would get inquiries from catalyst manufacturers, tube manufacturers, end users and operators to help support their tube wall temperature gathering process. We also then went into the ethylene space, so we've applied similar technology to the radiant section of ethylene steam crackers. And then also, as we've expanded the temperature range, we have processes on crude distillation units and other refinery fired heaters. So that means that we've got experience on side fired, terrace fired, top fired, bottom fired, cylindrical heaters. And that experience is growing over time as we get more interest from the industry. I just want to cover 3 infrared basics because it will help the understanding of the webinar. Emissivity is best understood, in my experience, as 1 minus reflectivity. When we talk about tubes in a fired heater, that emissivity changes over time. So emissivity is the ratio of radiation to a black body. So we might refer to the tube emissivity at 0.85 or 0.86 when installed. And that will change over time as the reflectivity increases or as the oxidation increases on that tube surface. So we need to understand the emissivity of the tubes, and we have ways of doing that. So essentially you'll see that some of that radiation in the tube is emitted, some of that is internally reflected. Black body radiation is 1, and that's a theoretical value. Background radiation is an interesting topic in fired heaters in petrochemical spaces. That's where we have a hotter surrounding, and we refer to it as incident radiation. So we need to consider incident radiation when we're, for example, measuring tube wall temperatures, because some of the radiation we're measuring with our pyrometer or with our thermal imager is incident radiation. So we need to compensate for that, and we can do that in all of our instruments. Sight path is dependent on the furnace atmosphere. So what we're looking for is high transmittance. That's where the infrared energy from the tube or from the background can travel through that atmosphere without any of that infrared energy being absorbed by the molecules in the atmosphere, CO2 or water vapor. So that sight path does shift depending on the atmosphere, but what we're looking for is the transmittance, and we tend to get that in the 1 micron range and in the 3.9 micron range, but that does depend on the furnace atmosphere itself. The handheld pyrometer for spot measurements, this is the Cyclops pyrometer. This is really why AMETEK Land is in this space, and this is where we're very well known. The Cyclops is being sold to the industry for more than 30 years. We have a 1 micron and a 3.9 micron pyrometer. Essentially, an operator goes around the reformer through the PEEP doors, takes recordings, and then they get raw values in a table or a spreadsheet, which are then corrected using emissivity and background settings. That then goes to a process engineer who will decide what decisions to make on the furnace or the fired heater in terms of activities on burners or looking at tube nipping based on what the temperature values that come back are. So it's a very manual process, and it requires some understanding of the infrared basics that we talked about. One effect that I just wanted to talk about quickly is PEEP door cooling. This needs to be considered because if your PEEP door is cooled 30 to 40 degrees during your measurement, you're not really getting a realistic value of what the tube is seeing when the PEEP door is closed. So whenever we take a survey, whenever we're demonstrating the instrument, we always check with the customer what that cooling rate is. And that, in our experience, has varied from 5 degrees. Sometimes there's very little cooling depending on ambient conditions, but sometimes that can be 40 to 50 degrees C if the ambient conditions are right. So that's something that really needs to be understood. That's best done on a tripod with the Cyclops being still and pointed at a fixed location on the tube. This is also important for the thermal imaging application. So you can do the same thing on the Borescope thermal imager to make sure that you understand what the conditions are and how they change when the PEEP door is open. The Gold Cup is something we're also very well known for. We're the only company to make such a device for the petrochemical industry. It's a 9-foot, 3-meter long, 50-pound, 20 to 25 kilogram water-cooled probe. So it's not something you're using every day. It's something to be used maybe on a quarterly basis. But this gives us our reference temperature values. And so going back to those 3 variables that we're concerned with in our fired heaters, emissivity, background, and sight path, the Gold Cup eliminates those variables by holding a gold hemisphere against the tube surface. So it's not a contact thermocouple. It's still a non-contact pyrometer, but you're holding that pyrometer right up against the tube surface. That means that that pyrometer does not see any background radiation. You're temporarily shielding it from that. It doesn't see any sight path interference because there are no gases in between, or very few gases in between the gold hemisphere and the tube. And the gold hemispheric design is designed to enhance the emissivity to nearly 1. So it's a near black body condition between that pyrometer and tube. So we can determine the emissivity by calculating the temperature deltas between the Gold Cup value and the pyrometer value or the thermal imager value. Another important thing to remember with the Gold Cup is that once you're holding that probe against the tube surface, you will start to see cooling. That's what you can see at point D on that chart. The point C is where the tube has made contact or very close contact with where the probe has made close contact with the tube. Point D is where the tube starts to cool. So we need to make sure we take our reading at point C, then we've got nice reference values. The chart on the upper right shows what you might typically see during a Gold Cup survey, and our values are generally a lot lower than what customers are reading with their pyrometer or thermal imager. That means that their emissivity settings or background correction settings that they're using with their infrared devices are conservative. And that's generally an industry practice to make sure that tubes are not overheated. But if you're not overheating tubes, you can typically run them hotter than you might be running them to get an increased yield from the fired heater in many cases. Portable thermal imagers is something we started to look at a couple of years ago based on the demand from the industry to take surveys. And surveys are increasingly popular throughout the industry because of that, number one, fear of overheating tubes, but number two, the need to increase the efficiency and balance the reformer in real time or fired heater in real time. And what we wanted to do was keep the benefits of the Borescope technology and also add some convenience to that. So we developed an air-cooled system. So that's purging the lens with up to 300 litres a minute of air. In many cases, 100 litres a minute of air is fine. But we do that because we want to keep the tip temperature low. We have a heat shield also, which actually is more effective at stopping air ingress into the fired heater than it is as a heat shield. In some cases, it is important to have a heat shield for safety reasons, but in many cases, you don't need a heat shield, but it's nice to prevent that air ingress, again, going back to the PEEPDOOR cooling effect. We see a growing market for this product, which is why we've developed a range of lengths, lenses, wavelengths, and accessory options to support this application. The range of our products means that we can cover a wider range of temperatures, and we also have a wider range of resolutions. And that means that you can, with this full range, cover different sizes of fired heaters. So in a certain size of fired heater, say a smaller fired heater, you may not need that ultra high resolution, and you may not need a narrow lens. You may need a wide field of view so that you're covering the whole space, and you may be able to use a 640, for example, by 480 pixel camera. I'll go through the terminology briefly. MWIRB for us means mid-wave infrared borescope, 640 being the resolution. NIRB means near infrared borescope, again 640 resolution. MW is mid-wave, that's generally 3.9 microns. NIR is near infrared, that's generally 1 micron. And obviously we do cameras for the longer wavelength as well. They would generally be stationary or fixed instruments, not on a borescope lens. The borescope lens is really useful when you have a PEEPDOOR or when you have a difficult to access port and you need a lens on the end of a probe. So that's particularly relevant for a lot of furnace applications. Those stationary images, again, typically for lower temperature applications, up to 1000 degrees C though, but you would generally use those when you're looking at a shell temperature or surface temperature without needing to go into that process. So we have that range from, say, 300 degrees C right up to 2000 degrees C for petrochemical processes. These cameras are tested in glass melt tanks. So we've got very long list of references in glass melt tanks which operate in that 1800 degrees C range, meaning that the petrochemical processes that we're working with are typically less challenging than some of the other industrial processes that we work with. But it's great that we can now cover that full range. So the portable system is essentially an accessory kit, which means you can use any of those Borescope cameras with. So the tablet is supplied with the software pre-installed. We supply all the air hosing, all the cables. We supply the filters, the regulators, the batteries. So you really don't need to add anything to this kit. Fittings in BSP and MPT for international compatibility. There's a stand there which is designed for easier maneuverability, but that's optional. So you can just order a flight suitable kit, which means that system is easy to travel with. And we've seen an interesting variance between customers that use this on one site. So they might have that stand up on the reformer, again, easy connections, And it's slightly easier because you've then just got a couple of meters of tube and cable to maneuver the camera. And then the more field-based operators or inspectors that want everything in a convenient pellet case. So we've tried to design the system so that it's applicable for both types of user. The software is a key part of this. The software is designed for easy data collection, easy data correction, so that we can easily input our emissivity values, our background temperatures, and we can use a real-time region of interest. So we can use the actual regions of interest to correct our raw data values, so minimizing the potential for human error in that correction. And then clearly the analysis. So we need to make it easy to export that data, export images, export videos into your reporting software. And you can have multiple emissivity settings, background correction settings. There's really not a limit, practically speaking, to what you can do with that software in terms of the number of regions of interest you can use. And like I said, we need to make that easy to export those datas, videos, and image files. The survey reports, again, increasing market for this. Operators and inspectors can use the corrected ROIs from the thermal images to create a thermal profile of the fired heater. So that's what you can see in that image, where hot tubes are identified, cooler tubes are identified and trended, and then we can look at the temperature gradient of the tubes vertically. So what you see on the larger image on the left-hand side is across a single plane. That would be, say, the maximum tube temperature measured across a single plane. So that's more like replicating your Cyclops or your fixed pyrometer type of survey. But then on the right hand side, you can see the vertical profile. So that's a key differentiator between a handheld Cyclops, again, lower cost instrument, to a higher cost portable Borescope thermal imager. You can really, because you're right in the process, you can really see the vertical temperature gradient, which is a unique property of the thermal imager. And that gives you a real good idea of where the reaction is taking place, where there might be issues with catalyst or flame impingement. So overall, we can identify the hottest and coldest tubes, improve balance and efficiency of the furnace, and also reduce the risk of tube failure. As we've developed the range, we've increased the resolution of the cameras. In the petrochemical space, we typically use the 640 by 480 pixel resolution cameras, NIR and MWIR. And you can see the difference in pixel resolution between a 320 by 240. These are both with a wide angle lens. We can also offer a narrower angle lens, which will give you better resolution further away from the camera. Again, you'll select those lens types based on the design of the fired heater. But you can see the increased resolution really gives you a huge number of pixels on tubes close to the camera. And then we've also found some interesting applications where you can get the Borescope into ports that you would not normally be able to access with a conventional camera. And that gives us the ability to measure collector temperatures or pigtail temperatures. And these are areas that suffer from failure commonly. And it's been useful for a few of our customers to be able to measure the temperatures of that and look at the condition. On the right-hand side, you see the video showing the operator inserting the camera into the PEEP door. And it's interesting to see how many tubes we can measure from a single image. So in terms of producing that report and the ease of producing that report, we have a calibrated radiometric thermal image. And in a single frame, you can see a huge number of tubes. So that would be very easy to identify vertical gradients and those hottest pixels, which tell us what the hottest tube temperatures are. So those tube metal temperatures to a cracker furnace operator are really critical. As the gas heats up from the inlet to the outlet, they really need to know so that they can optimize the decoking interval what those temperatures are. And as those tube temperatures increase, as you get closer to the end of your run length, you really need to know. And the camera is really useful in enabling customers to do that very quickly and easily. And then you've got an image archive which you can take back to process engineers to analyze in real time. So as you progress through the process over the number of days, you've got really usable data to make decisions on how you plan your production. I talked about the different lens options, so this is an interesting visualization of that. On a top-fired steam methane reformer, again, these are pretty large pieces of equipment. I tend to recommend in many cases that customers go with a 44-degree lens, but it does depend on the proximity of those near tubes to the wall, because in some cases you want a wide-angle lens so that you can get those, say, difficult-to-measure tubes. But what you get with a 44-degree lens is better resolution further down the reformer. And in some cases, those tubes closer to the middle of the furnace are quite difficult to measure. So with a 44-degree lens, you can get good resolution on those. And you can see in this case on the furnace being measured, there are hot bands, possible flame impingement, but with the 44-degree lens, we can actually get pretty good resolution on the burner tile, and we can see what's happening with the burner. And we can see some very elevated temperatures around some of those central burners, around the refractory above that, and that helped us identify some issues with that reformer. Again, 90-degree lens on the right-hand side and a top-fired reformer, good images, but further down the reformer, the pixel resolution is slightly limited, and that's what we need to consider on some of these, what I would say, very large reformers, which we see a lot of in the Middle East. This slide shows some interesting frames that we captured during some recent surveys. So you can see in the top left-hand side, there's some tubes significantly over 950 degrees C. Again, those would have looked hot to a Cyclops operator, so the operator carrying around the portable instrument may have spotted those hot temperatures, but he may not have spotted the very significantly elevated temperatures where that maximum heat flux is. And we saw with the thermal imager, but that was over 950 degrees C, obviously very concerning to that end user. On the bottom left-hand side, on a terrace wall reformer, we saw some air leaks around the burner tiles, some pretty significant ones. And actually what we saw on the top right-hand side is the same furnace where we saw an issue with tube leaks, and that was producing a huge amount of air ingress and really having an effect on those tube temperatures. That actually may not have shown, again, from the Cyclops. Customer may have been able to see that visibly with the lower tube temperatures towards the top of the furnace. But we were able to identify just how low those temperatures were, in some cases lower than 650 degrees C. So really concerning. But by fixing that issue, by addressing those tube seals, the customer spotted a real reduction in their fuel consumption. So they're really able to improve the efficiency of that process, which again is a key priority at the moment. The bottom right-hand side image is something I like to use for training a lot. It shows the gold cup being inserted. So you can see that we've put the gold cup on that third or possibly fourth tube. And it's interesting as well. It shows how effective the cooling of the gold cup is, because you can see the very low temperature of the gold cup itself. But actually, interestingly, that gold cup surface is polished. So we do see reflections of other tubes. So the gold cup surface temperature may look high, but that's because it's seeing reflections of other tubes. So it's a nice example of incident radiation. We wouldn't obviously consider those high tube temperatures the temperature of the gold cup surface, because we would correct for background correction. We would correct for emissivity, sorry. So we know that the tube surface or the probe surface is very reflective. Therefore, we know the emissivity is low. And we correct the value so that we know that the surface of the gold cup is actually very low temperature. On these images, you can see other phenomena that we spotted using the camera. So refractory damage, that shows us a cold spot because you can see the cold air ingress. Again, very low temperatures in a place that you should only see very high temperatures. We can identify the temperatures themselves of hot spots versus just knowing that they exist. We can see things like surface scaling and carbon formation on the surface of tubes. Flame impingement is a common phenomena as burners age and as the condition of those burner tips deteriorates. And you can see that really significantly in that one image where those tubes closest to that sidewall are suffering from very high elevated temperatures, and then the tubes further away are very, very cool. So the balance of that fired heater was very poor. And then, like I said, we can look at hot bands and the potential elevated temperatures that they're suffering from. In this case, on a steam cracker, we could plot the vertical temperatures because there was an issue with decoking and potential concerns with very high surface temperatures. So we were able to look at that, plot those temperatures vertically. And then on the right-hand side, we were able to look at single point temperatures and compare those to Cyclops readings. And we saw very close correlations between the Cyclops readings and the same wavelength infrared thermal imager in this case. And of course, you can use the same camera in the portable Borescope system on a fixed process. So you can install the cameras permanently, as you can see on the bottom right-hand side, to continuously cover a reformer or fired heater to provide real-time temperature data to a DCS. And that will give you the ability to monitor an alarm in real time continuously, optimize in real time. And like I said, it's the same camera used in the portable system, just in a fixed water or air-cooled application. But we think of this more as a system than a single product. So the software is really critical to that. And what you'll see over time is more customers adopting fixed systems as the software improves and as the algorithms improve. The pattern recognition algorithms are able now to identify tube failures a lot sooner than what an operator might be able to do. So as you see improvements in that data science side, you'll see more customers adopting this type of technology, I'm sure. And so that's where this question comes in. How do you turn thermal imaging streams and billions of temperature data points into cohesive automated system that optimizes furnace monitoring and control? And that's the challenge to the industry now. How do we take this very advanced technology in terms of imaging and data collection to provide more usable, useful, intuitive reports, dashboards, trend charts for end users? Because at the moment, the number of data points is really difficult to analyze by a single engineer. So that needs to be done by software. And I think longer term, there's a challenge to close the loop, essentially. At the moment, on fired heaters in the petrochemical and refinery space, there's not a lot of closed loop control between the temperature or infrared temperature devices and the actual control systems on the furnaces. So again, as these software applications improve, I expect to see more closed loop control systems. So just to quickly recap on the benefits to the two main types of fired heaters that we've applied this technology to. An ethylene cracker's remote real-time monitoring of coils, burners, tube metal temperatures means a centralization of furnace inspection. We can safely increase production capacity, reduce maintenance costs by preventing tube rupture and extending tube lifetime, more efficient and controlled process with more uniform tube metal temperatures, better fuel efficiency, less coke formation, and we can prevent downtime, unplanned shutdowns, incidents, and increase the overall safety. On steam reformers, we can increase the reformer capacity without risking tube failure. We can prevent catastrophic incidents, extend tube lifetime based on actual information, and we can improve plant safety, reduce running costs, and implement predictive maintenance. On other types of fired heaters across refineries, we're still learning about what the potential benefits of the technology are, and we're really interested in working with those end users to help implement the technology on a wider range of fired heaters. So I hope this has been a relative introduction to the technology and how we're using it on fired heaters. If you do have any questions, please feel free to get in touch. Thank you.
James, thank you so much for that great presentation. For all of our attendees, all questions will be answered following today's webinar. If you have a question for us today, please go ahead and enter it into the Q&A window and hit submit. James will get back to you with an answer. I will give you some time to enter your questions right now. Thank you for all those great questions. I will give you another few seconds to submit any questions. All right, thank you everybody for those questions. You're also going to be receiving an email from us with a link to the on-demand version of this presentation. You will be able to come back and watch this again or share it with colleagues. Lastly, please take a moment to complete a survey which will appear on your screen at the end of this webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you so much for taking time to attend this webinar event. Take care, and we will speak with you soon.